H2S. And so we'll just put a 2 right there. That way everything should be balanced. We put in the states of matter. We have AQ, let's say. This might be actually a solid now that I think about it. I think that might be a solid. Let's see. It is a solid. Yes, it is a solid because sulfides are usually going to be insoluble. And we have HCl, which is going to be aqueous. ZnCl2, as long as it's not silver, mercury, or lead, it's going to be aqueous. And H2S is a gas. H2S is a gas. And so this is our molecular. Let's do our ionic, where anything that is aqueous is going to split apart. Anything that's a solid or a gas is going to stay the same. So that's ZnS with a solid plus 2H plus 2Cl minus. Both of these are aqueous. And that's going to go to Zn2 plus, which is going to be the aqueous form, plus Cl2Cl minus, aqueous. And that goes to, and then we also have to add the thing that is going to be also not aqueous, which is H2S. It's going to be gaseous. Okay, so that's our ionic equation. Now we need to cancel out everything that is on both sides, which is just this 2Cl. And so our net is going to be ZnS S plus 2H plus goes to Zn2 plus H2S. This is a gas. And this is our aqueous. And this is also aqueous. Okay. And so we can see that exact same thing here. ZnS plus 2HCl goes to ZnCl2 plus H2S. We're going to write the ionic equation, splitting everything that can be split into ions. We'll cross out the things on both sides, and we're left with the net ionic equation. Okay. So let's go ahead and work on oxidation numbers. So these are very similar to how a charge is described. And we're talking about the actual charge of an atom if it exists by itself. And so we can use simple rules to define this, but basically it's another name for the charge of an atom. So rule number 1, if you have an element, the oxidation number is going to be 0. If it's just by itself, so that is going to be any element that you pick on the periodic table, the oxidation number is 0, any of them. Monoatomic ion, so that means one atom, the oxidation number in a monoatomic ion is going to be equal to the charge. So if you have H plus, the oxidation number equals 1. If you have H plus, the oxidation number equals 1. If you have Zn2 plus, the oxidation number equals 2. And this could be a +1 and a +2. That's fine. For oxygen, the number of oxygen is going to be the oxidation number of oxygen is going to be -2 for most of the compounds, except for if you have hydrogen peroxide or any other kind of peroxide. That's because it looks like this, HOOH. And really what this comes down to is what these atoms are bonded to. So since you have two atoms bound to each other, that is going to negate one of the charges, one of the oxidation numbers. And so each of these is going to have a -1 charge, when it normally would have a -2 charge, but since they are bound together, then there's no difference in charge, and so we can just say it's -1 for both. Hydrogen is the oxidation number. The oxidation number is usually going to be +1. There are certain scenarios in which you will have an oxidation number of -1, and that's going to be when you have a hydride. So that's going to be when it's bound to a metal. If it's bound to a metal, that means it is a hydride. If it's bound to a metal, it's a hydride. Halogens, for most of them, if they're bound to a metal, it's going to be -1. If the other element is another halogen, if it's a different halogen, then it is not going to be the halogen above it in the periodic table. That means it's not going to be 1. So for example, if we have F, Cl, Br, and I, this is the order that they're in on the periodic table. If you have I, Br, then the one that is on top of it is going to win. So this would have a -1, this would have a +1. If you have BrCl, this would have a -1, and this would have a +1, and so on and so forth. Compounds and ions, the sum of the oxidation numbers of the atoms in a compound is going to be 0. But if it is an ion, then it's going to be the charge of the ion. So if you have NaCAN, something like this, nitrogen is going to have a -3 charge, and calcium is going to have a +2 charge, sodium is going to have a +1 charge, or oxidation number. And the reason that I know that is because sodium and calcium always have the same charges. Nitrogen usually has the same charge, especially when it's bound to a metal. It's going to have the same charge. And so that is that. But also, there's no charge up there. There's no charge, so you can assume the charge is 0. And so all of the values have to add up to the same number. And so we can do this splitting thing where I have an N on one side, we'll put a -3 there, and then whatever is on this side has to equal to +3. And so sodium is going to be a +1 because of where it is on the periodic table. Calcium is going to be a +2. And so 1 + 2 = 3. That we're going to add that together, and then that will balance out the charge. However, if you have something like SO4 with a 2- charge, so polyatomic ion, then we will have something a little bit different. So oxygen is usually going to be a -2 charge, except for when you have peroxide. Since sulfate is not a peroxide, it's not HOOH or NaOONA or something like that, then we have a -2 charge. So the overall charge is going to be -2 times the number of oxygens that there are times 4, which gives us an overall -8. And keep in mind, we have a -2 or a 2- charge, a -2 charge on the right-hand side already. So whatever the charge of sulfur is going to have to be such that the overall charge is going to equal -2. So +6 plus the overall charge on the negative side plus -8 is going to be -2. And so we have to have the entire left-hand side equal to -6, not -8, because the overall charge for the entire polyatomic ion is -2. And so that's just going, +6 is going to be what we have over here. So the oxidation number of sulfur is +6. So let's get into some examples. Go ahead and try this one on your own. For ClO3, remember, oxygen will have a -2 charge, except in peroxide, so H2O2 or something like that. Okay, so let's go through it. So using rule 6, oxidation number of Cl. So this is how we're going to add them together. We have the oxidation number of chlorine plus 3 times the oxidation number of oxygen is going to be -1. So let's do it like this, ClO3 with a -1. The overall charge on the right-hand side, or the overall charge for the entire molecule is going to be -1. Oxygen is going to have a -2, and we'll multiply that by 3 to give an overall charge of -6. And so if the overall charge on the right-hand side, RHS, is -6, we have to have something counterbalancing that, but with just enough to leave a -1. So what plus -6 equals -1? That's going to be +5. Chlorine is going to have a +5 charge, and that's what we see right here. So -1 minus 3 times -2 is going to be +5. The oxidation number of chlorine is +5. Okay, give it a shot, and let's continue. Remember, you can take a look at the rules if they would help you out. Okay, so gold, Au, is by itself. There's no charge given, and so it's going to have an oxidation number of 0. On equals 0. Chlorine is by itself. This is going to be molecular chlorine. So there's a few diatomics, and what that means is diatomics are going to be O2, N2, F2, Cl2, put commas there so they're not together, Cl2, I2, Br2. Those are your diatomics. All diatomics have a 0 oxidation. All diatomics have a 0 oxidation number. Let's go through phosphorus, PF5. So phosphorus in PF5, that's phosphorus pentafluoride. We have P and F5. I'll split it down the middle. Each of the fluorines is -1. And we will multiply that times the 5 fluorines that there are. That gives us an overall charge of -5, which means to counterbalance that, we have to have a +5 for fluorine. So it's going to be a +5 On. Sulfur in H2SO4. We kind of already did this, but let's do it again. H2SO4. This one's a little bit more complicated. So oxygen is always going to have a -2 besides in peroxide, so that's -2 times 4. Hydrogen is always going to have a +1 when it is going to be, -8. Hydrogen is always going to have a +1 when it is not bound to a metal. When it's bound to a metal, it has a -1, so it's going to be +1 times 2. And so that gives us a +2 plus some number is going to be equal to +8. And we know that it's going to be just some number to equal +8 because there's no charge up here anymore. So +2 plus some number is +8. That's going to be +6. So +2 plus +6 equals +8. And so S has a +6 oxidation number. Okay, let's talk about redox reactions. I teased this a little earlier, but it's important to know these ones. So redox reactions are when you have electrons that are going to be exchanged between elements. We can abbreviate them as this from now on. And so we can also do this in equations. So for example, Na, which you're about to see, Na going to Na plus, we can use this as a reagent or as a product in this case. So electron, there we go. That way the charges are going to balance. Charges must be balanced on both sides of the equations every single time. For this to occur, the charge of an element must be different when comparing the same element in the products and reactants. So over here we have elemental sodium. Over here we have ionic sodium. It goes from a 0 to a +1. So the oxidation number has changed, which means that this is a redox reaction. A half reaction is what I just drew. So a half reaction shows something that is being oxidized and something that is being reduced. And I'll get into what those terms mean exactly in just one second, but we have Na going to Na plus E minus. This is a half reaction because it is 1/2 of an oxidation reduction reaction or a redox reaction. Redox comes from redox, reduction, oxidation. And so you must have the gain or loss of electrons in a half reaction. And so this is the definition. So an oxidation is when the half reaction occurs and you are going to lose an electron. Oxidation is loss of electrons. Reduction is when you have a half reaction and then you gain electrons. So reduction is gain. Oxidation is loss. Reduction is gain. And we'll get into what oil rig is in a moment as well. And so when you're doing these reactions, it's important to be able to identify what the whether or not you have a redox reaction, because that is going to change how you approach it. And so you have aluminum in its elemental state, which means it has a charge of 0. Chlorine, the diatomic, in its its molecular state, which we have as a 0, going to aluminum, which is going to be a +3, and chlorine, which is each one is going to be a -1, and there's 3 of them, so that is -3 overall. H3PO4, however, the H+, this is phosphorus acid, so that's going to be a +1. If it's an acid, then hydrogen is going to be in the +1 state. Oxygen is going to be in the -2 times 3 state, and so we'll put a line down the middle. We'll get a -6. We have +1 times 3, which gives us a +3 for all the hydrogens. In order to get to +6, we have to add 3, which gives us +6. And so the oxidation state of phosphorus is going to be +6. So we have a +1, we have a +3, and we have a -2 for all the oxygen, or for each of the oxygens. Potassium is going to have a +1 oxygen when it's bound, when it is in peroxide, has a -1, but it is not in peroxide, it's just in hydroxide, so it has a -2. And hydrogen is going to have a +1 because it's not bound to a metal. Over here we have the same thing, +1. We have a -2. Over here we have a +3. And here we have a -2. And so the difference between these two, this H3PO3 and K3PO3, is that the hydrogens and potassiums have switched places. And I'm actually going to erase this because that's not true. They've switched places, which means, but the charges haven't changed, right? Hydrogen has the same charge as potassium. So we know that the charge for potassium is going to be +3. And so this is not a redox reaction. None of the charges change. We have oxygen going from a -2 to a -2 and a -2, same thing, -2. We have hydrogen staying as a +1 throughout. Hydrogen stays as a +1. Potassium stays as a +1. And phosphorus stays as a +3. And so this is not redox. In fact, acid-base reactions are very rarely going to be redox reactions. However, for the one above, this is a redox reaction because we have 0 going to a +3 for aluminum and 0 going to a -1 for chlorine. So this is a redox reaction. Okay, so I'll give you a second. Go ahead and try these out. Identify which ones are going to be redox reactions. Okay, let's get into it. Sodium is a 0, but over here it's a +1. And I'm not going to go through exactly how to identify these. I'm going to just do this really quickly so we can move on. But this is the loss of electrons. When it's by itself, it's going to have a 0. When it's with something else, it'll have a charge. So it's going to be a 0. We have oxygen, which has a -2. We have hydrogen, which has a +1. Over here, we have oxygen with a -2. We have hydrogen with a +1. And now we have elemental hydrogen. Oh, let me go back and correct this. H2. That's the other one that is a diatomic. Okay. And we have, so we have hydrogen going from a +1 to a +0. We also have sodium going from a 0 to a +1. So this is a redox. Anytime you have something that is reduced, you also have something that is oxidized. Any reduction must also have an oxidation. Sodium was oxidized and hydrogen was reduced. Now, samarium and iodine. Iodine is going to be a -1 times 3, which makes samarium a +3. Potassium is a 0. Samarium 2 iodide is going to be a -1 times 2, which gives samarium a +2. Potassium is a +1 now, and iodine is a -1. And so this is going to be a redox as well. That's because potassium was oxidized, samarium was reduced. And H2SO4 and KOH, again, this is an acid base. So we should assume, we should guess right off the bat, since it's an acid-base reaction, that it's not going to be an oxidation, but we've already done this. So sulfur, this is going to be a -2, hydrogen is going to be a +1, and sulfur, I believe, is a +5. Let's go back and look real quick. So we know exactly what it is. Sulfur was a +6, my mistake. And so we have a +6 over here. Sulfur stays as a +6 on that side. Oxygen is a -2. Oxygen is a -2. Hydrogen is a +1. Hydrogen is a +1. Potassium is a +1. Oxygen is a -2. There's no change. It is not a redox reaction. Okay. So a little bit more terminology. Oxidizing agents and oxidants are reduced. So what does that mean? If it's a species that oxidizes something else, then it itself is being reduced. So let's say that we have Na +1 plus K with a 0. That's going to end up being Na0 plus K plus 1. And so this is going to be donating an electron, and this is going to be accepting electron. And if we go by O, oxidation is loss, and reduction is gain, is gain. Then oxidation is lost. The thing that lost an electron is oxidized. The thing that gained an electron is reduced. So if it is reduced, it is an oxidizing agent, which means it oxidized something else. So, oh my God. Na is the oxidant. Na is the oxidant. And now the opposite is true for this. So a reducing agent is going to reduce something else, which means that it is going to be oxidized. So potassium goes from a 0 to a +1. Oxidation is loss of an electron. So potassium was oxidized, which means that K is the reducing agent, oxidant, reductant. So it's confusing, but things that are reduced are oxidizing agents. Things that are oxidized are reducing agents. And so let's just go through this again. So there's two different ways you can memorize which one is going to be, which is oxidized and which one is reduced. And I have gone through them a little bit already. So I'll start with oil rig. So oxidation is loss of an electron. Reduction is gain of an electron. Loss of electron is oxidation. Gain of an electron is reduction. And feel free to use either of these. Loss of an electron is oxidation, gain of an electron is reduction, or oil rig. Leo the lion goes grr. That's how I remember that one. And so, yeah. Okay, so there are a lot of different oxidation reduction reactions that are present in our everyday life, but here are the different types of oxidation and reduction reactions that we have. We have combination reactions in which A adds to B and becomes AB. We have decomposition reactions in which AB goes to A plus B with charges. Let's say that this is 0 and 0. This would be 0, and then we'd have a it'd be a 0 and a 0 still. And then we have single and double displacement reactions. So that is AB plus CD goes to AD plus CB, double replacement. And then we also have single replacements where we have A plus CD goes to goes to C plus AD. We also have combustion reactions. This is where you get CXHYOZ going to, and X, Y, and Z, those are just placeholders for numbers, plus O2 goes to CO2 plus H2O. We've covered combustion reactions quite a bit, but this is also another oxidation reaction because we have oxygen with a 0 charge going to oxygen with a 2- charge. So something else, this was reduced, oxygen was reduced because it, the way that you can think about it as well is that reduction of positive charge. So oxygen didn't have a positive charge, it didn't have a negative charge, it just had a 0 charge. But it didn't go into the increasing of the positive charge, right? It didn't go to O plus 1, it went to O2 minus. So that was a reduction of the positive charge. And so that's how we know it was reduced. Okay, now I'm gonna skip these for now because these are already on YouTube, but the slides are up so you can look at them yourself. Okay, so let's talk about a combination reaction. We have two substances that combine to make a third. Both of these are going to have oxidation states of 0. Then we get a +1 and a -1. So we can then say that sodium lost an electron. So LeO lost an electron. It was oxidized, which makes it the reducing agent. Chlorine was reduced, which makes it the oxidizing agent. And so this combination reaction is when we have two things becoming one. We have Na and Cl becoming NaCl. And so this is what this looks like on an actual scale. Sodium is this really soft metal. It's kind of the consistency of butter. And then chlorine is going to be just a gas. It's a green gas. And when you combine them together, you end up getting NaCl. And it will react very violently to make NaCl. A decomposition reaction is basically the opposite. And so I've written this before on the board, but this delta, this is an uppercase letter delta. And what that means is this means change. You're going to see this quite a bit moving forward. Change. The delta means change, which means specifically, we're talking about a change, delta H, which means change in heat. But we can do the same thing here. So I want you to do this on your own. Which one is the reducing agent? And which oxidizing? Okay, which one's the reducing agent? Which one's the oxidizing agent? I'll give you a second. And keep in mind that we can separate this into Hg2 plus and O2 minus to figure that out. Okay, so this is a decomposition reaction. It's the opposite of a composition reaction? What do we say? Combination reaction. It's when you take one substance and make it into two. The oxidizing agent is going to oxidize something else, which means it's going to raise the positive charge. And so if we had a 2 plus going to a 0, that would be a reduction. And so it's going to raise the positive charge of something else. So 2 plus going to 0, we can write the half reaction here. If you ever can't figure this out, write the half reaction. Hg2 plus 2 electrons goes to Hg with a 0 charge. O2 minus 2 electrons goes to O. And I only drew one of the oxygens because whatever. It doesn't matter. We just need to know which one's going to be oxidized and which one's going to be reduced. Oh, that's not how you write that. You write it like this. O2 minus goes to O plus 2 electrons. This has a 0 charge. 2 E minuses. And so if you have something that is going to lower the positive charge or raise it. So we have L EO. Lose electrons is oxidized. So this one was oxidized, which means it is the reducing agent. Which means that this one must have been reduced. Which means it is the oxidizing agent. Okay. And so this is a visual example of this. So you have oxygen 2 minus and mercury 2 plus that are splitting apart, and then you have O2 and Hg metal coming out. And so it's going to look something like this, where you have these little beads of mercury that come out of this. This yellow substance, this orange substance is mercury oxide. Okay, a displacement reaction we've already covered. This is a single displacement reaction. You should know the difference between single and double displacement reactions. Those are going to be pretty important. But a displacement reaction is when you have these two switching spots. And so zinc goes from a 0 to a 2 plus, which means that it is oxidized. Zn is oxidized. And then you have H plus going to H with a 0, which means that H is reduced. The positive charge of H has been reduced, which means that zinc is oxidized. And chlorine is going to stay -1 throughout. And so this is what this would look like as well. You have zinc metal being put into liquid, where there are chlorine atoms coming together. Wait a minute. Yes, you have chlorine atoms coming together, and these are going to help dissolve the zinc atoms and take them into solution, where you have zinc being surrounded by water atoms and chlorine being surrounded by water atoms. So you get zinc chloride out. A combustion reaction is when you have a substance. Usually this is going to be a carbohydrate. Carbohydrate. So something with carbon and hydrogen in it that reacts with oxygen and is going to become CO2 and H2O every time. And so what was being oxidized, what was being reduced, it's a little less clear in this. And so let's say that this is going to be a plus, this is going to be a +1 times 10. We have a -4 times 4. Well, no, it has to cancel out. It has to cancel out, and so the overall charge is going to be -10 on that side. And it goes from a negative charge to a +4. We don't exactly know. As I said, these are going to be a bit more complicated, and it really helps if you are able to draw these things out. I wouldn't put this on an exam, though, because it's going to be a little bit more complicated than what you're seeing right here. This could be a negative charge, but it's not exactly clear what that negative charge is going to be. So I'm not going to speculate. But if you wanted to see that, a combustion reaction in real life, this is a piece of steel wool that's burning. And so what happened is, in the presence of heat and oxygen, this metal chunk is going to make iron oxide, which is rust. Iron oxide is going to be oxidized, and it's going to turn into iron oxide from iron. So this was oxidized. Oxygen had a 0 charge, and now it is reduced. Okay. And so we're going to talk about balancing these reactions, these oxidation reduction reactions, and we're going to use half reactions to do so. But first, I've showed you many examples now of how to identify what is oxidized and what is reduced. And then we can balance the half reactions and combine them to obtain a balanced oxidation reaction. And so I intend to give you guys a lot more work on this because this can be very confusing, especially if you're brand new to balancing reactions. But this is important. When something is oxidized, something must be reduced. And when something is reduced, something must be oxidized. Okay. And so if we were going to do this reaction, we have zinc plus silver going to zinc 2 plus silver 0. Zinc is oxidized, resulting in zinc 2 plus, and silver is reduced, resulting in silver with a 0 charge. And so let's draw the half reactions for this. So I'll go back here so we can see them. But what you want to do is you want to isolate one of the reactants and its product, and then apply the half reaction rules. So zinc with a solid, as a solid, is going to go to zinc 2 plus E minus 2E minus. And you have Ag plus E minus going to Ag0, and this is 0 as well. And so when you're writing these out, if you don't know which side to put the electrons on, remember that charges must balance. So, for example, you have a net 0 charge. Zinc has a 0 charge, which means you must have a net 0 charge over here, which means if you have 2 plus, you have to add 2 minus 1 charges. Minus 1, 2 times minus 1. 2 plus 2 times minus 1. Let me rewrite that a little bigger. On that side, you have to have a plus 2. I'll put that in parentheses. Plus 2 minus 2 times minus 1 to get a 0 charge. The charge on the left must be the same as the charge on the right. Left charge must be the same as right charge. The left charge must be the same as the right charge. Okay, and so what we're going to do next is we want to balance the half reaction by adding electrons to the more positive side, etc. And then we're going to go back here for a second, and I'll explain what that slide says. So we have 2 electrons. Once you've balanced each individual half reaction, you want to balance the entire reaction to match the other one in terms of electrons. So if you have zinc producing 2 electrons, but silver accepting 1 electron, then we're going to multiply this by 2 times. And so that's going to end up with 2Ag plus 2E minus goes to 2Ag0. And so this is our new reaction, and now we have a balancing of electrons on both sides. And the next step is going to be written here. So this is exactly what it says. If you have 2 electrons being lost and 1 electron being gained, you need to multiply this by 2 in order to get those electrons to be the same. That way, our entire reaction is going to look like this. Zn 0 plus Ag. Once we combine these two again, we'll combine them, and then we will see that we have a 2Ag plus 2 electrons goes to Zn2 plus 2E minus plus 2Ag0. And these can cancel out, and that's how we are left with this final equation. So the electrons are going to cancel out just like we did with the net ionic equations, and then you would be left with one equation. Okay, So let's keep going. Let's use the half reaction method to balance this following reaction. And go ahead and try this on your own before we, I know that all the information is here, but let's try it on your own before I show you how. Okay, so step one is to write out the half reactions and balance them according to the electrons. You have Mg going to Mg2 plus, 2E minus, N2 plus 6 electrons going to 2N minus. And so we're going to have to multiply this by 3 because 2 electrons times 3 equals 6 electrons. And there's 6 electrons down here. In order to combine them, that's what we're going to have to do. And so this is exactly what we do. We multiply it by 3, and then we are left with 3Mg plus 6 electrons equals 3M plus N2 equals 3 Mg2 plus 2N3 minus. The electrons are then going to cancel out, and we're left with the balanced reaction here. And then we will recombine all of the ions, and we will get this. Okay, we're going to switch gears now and talk about something else. We've covered a lot this far, but this is another one of the more useful concepts for chemistry, and there's going to be a lot of math involved in this. And so we've discussed what a solute is. Just as a reminder, it is something that dissolves into a solvent. Now, a solution is going to be something with a solute dissolve. Okay, actually, I'll keep writing this, but I want to change it. So dissolved into it. So not just something, but specifically a solvent with a solute dissolved into it. And so what that looks like, if I were to draw it out, let's say that we have this container here. If we were to take, let's say it's full of water, I'll make it blue. Our water is solvent. The solute, let's say it's NaCl. This is our solute. And we want to know the number of moles of NaCl that are dissolved in the liters of water. Number of moles, and this is the number of liters. And that's how we'll calculate this. We'll just divide the moles by the liters. Okay, and so in the actual laboratory, this is what this looks like. You would measure out something. This is copper sulfate, CuSO4. And then you would put it into a container. This is a volumetric flask. And then you would fill the container with the solvent. And this is how you would make a solution. So you take the number of grams, convert it to moles, and you would record the number of liters. And then you would take the number of moles and divide it by the liters. And that's how you would get molarity, which is denoted as a big M. And so we can do a lot of math with these, with molarity. One of the things that we can do is a dilution. And so a dilution is when you take a substance and you change the amount of concentration. So we will be able to determine the amount of moles of something by multiplying it by the number of molarity, the molarity, whatever this big M is, and multiplying it by how much of it there is. So whatever the molarity is times the liters of solution, this is how you're going to get the moles of the solute out. And so we can rearrange this like this. Moles of solute is going to equal the molarity times the volume. Upon dilution, the moles of solute is not going to change. So if you took 10 grams of NaCl, you put it into a flask with water, you made a 10 gram NaCl solution. If you increase the amount of water, you add some water, you pour that in there, and now you have this much. The amount of NaCl that you added does not change. No change in moles of NaCl added. And so that's what we see here. Once you change the amount of volume, you can calculate a new molarity by using this equation here. But let's go back for a second and see that whatever the molarity is, if we multiply it by the liters of solution, we're always going to get the same number of moles. And so if we change the volume, we will just have a new molarity here, but we're still going to have the same number of moles. The same number of moles is going to remain. And so we can use this equation. MIVI equals MFVF. You can also say M1V1 equals M2V2, where 1 is starting value, 2 is ending value. Okay, and so on a visual level, this is what's happening. We have a molecular view of a solution of Cl2, and so let's just count them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and let's say that that is 10 moles, and let's call this 1 liter. 10 moles divided by 1 liter is going to give us 10 molar solution, which is equal to 10 moles per liter. If we add more solvent, let's say that this is now 2 liters of solution. We have 1, 2, 3, 4. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have the same number of moles, but twice as much solvent. And so this ends up being 10 moles divided by 2 liters, which gives us 5 molar. So we went from 10 molar to 5 molar. And we can also do that like this. Our M1, our molarity to start with, is going to be, if we didn't know what the molarity is of the second one, we could say that we have 10, or I'll write out the equation again. We have M1V1 equals M2V2. Our M1 is going to be 10 molar. Our V1 equals 1 liter. Our M2, let's say that we don't know it yet. We want to figure that out, but we do know that our V2 is going to be 2 liters. And so we'll write the equation down here because I'm running out of space up there, but let's say that it is I'll write the actual numbers. We have 10 molar times 1 liter equals, I'll use A times 2 liters. 1 liter and 2 liters. And we'll rearrange to solve for A. We'll say 10 times 1 divided by 2 equals A, which is equal to 5 molar. So either way is fine to do it, but it really just means the same thing. It really means that when you're doing a dilution, there are the same number of moles as when you started. That's really what the big takeaway is. And this is just a picture of some of the equipment that you would use to do this. Okay, so let's give it a shot. We have, go ahead and try this on your own, and then I will help. One thing that is important is that you have milliliters here. So convert to liters. Eventually, you will not have to do that, but I want you to do this just to get used to converting to liters and everything, and then we will continue. Okay, so if you have, let's plug in these values. Our M1 or Mi is going to be 14.8 molar. Our V1 or our Vi is going to be, determine how many milliliters of a solution of, oh, we don't know, so let's be a question. Our M2 or MF is going to be 1.00, and our V2 is going to be 100 milliliters, which we will convert right away. We can, there are 1,000 milliliters in 1 liter, and so that's going to be 0.100 liters. And so we get following this equation, we will get 14.8 times V1 equals 1.00 times 0.1. And we'll rearrange it as it does here, and we'll say that V1 equals 1.00 times 0.100. I didn't use the right sig figs before, that's okay. 1.00 times 0.100 divided by 14.8. And so when we do this math, I'll just do it real quick. We have 1 times 0.1 divided by 14.8. That gives us a V1 of 0.006757. And we can rewrite that as 6.75. This is a 3 sig fig problem, so we will say 6.76 times 10 to the negative 3 liters. Okay. And so 6.76 times 10 to the negative 3 liters. 6.76 times 10 to the negative 3 liters. For every 1 liter, there's 1,000 milliliters. That gives us this answer right here, 6.76 milliliters. So you can keep it in milliliters or you cannot. Just keep in mind that whatever units you start with are the units that you're going to end with. But I recommend just keeping everything in liters. That way you will not get confused. Okay, so if you are unsure of what you are doing, this is how you can check. The volume of the more concentrated solution will always be less than the volume of the final solution. So that means that we had 6.76 milliliters and we had a M1 of 14.8. The M2 was 1 and it had more milliliters. And that's what the second one says. The initial concentration in the solution is greater than the final concentration after. The initial concentration of a solution is greater than the final concentration after dilution. That is, the initial concentration of a solution is greater. Right, yes. So 14.8 going to 1, the initial concentration is going to be greater than the final concentration. All right. So that is the technique that we use for molarity. Let's talk about quantitative analysis. So this is how we would determine the amount of a substance or species that is present in a material. And we also have gravimetric analysis, and this is usually when we're talking about mass. We're converting the species to a product that can be isolated and weighed. And so let's give some examples of these. We have a reaction between an unknown amount of barium ion and potassium chromate, forming barium chromate. And so if we wanted to know how much of the barium ion that we started with, we would have to know how much of the barium chromate that we made. And so what we would do is we would mix it all and then filter out everything that is going to be aqueous. And so let's go ahead and write an equation for this. We have Ba plus Ba2 plus K2CrO4. This is going to be AQ and AQ. And we're going to make K plus, we'll make two of those, plus BaCrO4, and this is going to be aqueous, and this is going to be a solid, as we can see right here. That is a solid. And so once we do that, we're going to take all of the aqueous things. AQ will fall through. All aqueous species are going to fall straight through, and they're going to go right into the filter, and everything that is solid is going to remain. The precipitate. And so once we find out the amount of solid that we have, then we can see, by using the molar mass, we can see how much of the ion that we had to begin with. Okay, so this is a problem. I will give you a second, and then I will read it, and then we can go through it. Okay, so if you have a 1 liter sample of polluted water, and you analyze it for the amount of lead present in it by adding an excess of sodium sulfate into it, soluble, because it has a group 1 metal and it's a sulfate, the mass of lead sulfate that is precipitated is going to be this amount. What's the mass of lead in the liter of water? We'll give the answer as milligrams of lead per liter of solution. Okay, so we want to know how much lead is going to be in this lead sulfate. And so the first thing that we'll do is we'll take the molar mass of Pb, which is 207.2, and the molar mass of SO4 2 minus. And we'll divide them, multiply by 100, and you get this amount. So we'll then take the amount of lead sulfate that we got out of the reaction, multiply it by the decimal form of the percent of lead in there, and it'll tell us exactly how much lead we have in that sample. And so that'll tell us that the water contains 157.0 milligrams of lead per liter. Okay, and so this is another one. I'll give you a second to give it a shot. And actually, I would rather that you guys just do this one. I'm actually not going to go through it. I'm going to speed past it, but this is a good practice for you. So Allura Red has been found to have a concentration of 0.01 molar in red Gatorade. If the molar mass of Allura Red is the red dye in Gatorade. If the molar mass of Allura Red is 496.42, how many grams of Allura Red? This is a different type of reaction, but I will show you how to get it started. And so we can also use dimensional analysis to figure out problems like this. And so this is how we will start. Just like grams per mole, molarity is usually going to be a conversion factor because it has moles and liters. So we'll start with this. 250, this is the only one that is not a conversion factor, so that's what we'll start with. 250 milliliters, there's 1,000 milliliters in 1 liter, and we need to convert to liters because this is moles divided by liters. And we want to find out how many grams there are, so that's where we're going to end up. But the next step is we're going to use the molarity. So the molarity is going to be 1 liter, and on top we will have the number of moles, which is given right here, 0.01 moles. And so when we have 0.01 moles with some sig figs there, I just didn't include them for space. We can then use the molar mass. For every 1 mole of Allura Red, we have 496.42 grams. And that should give us actually our answer right there. So go ahead and give that a shot on your own. I'm going to continue. So volumetric analysis is what we'll be doing this week, actually. And so it's a type of quantitative analysis based on titration. And so the titration is a way that we are going, this is how we would determine exactly, we're going to use molarities and determine the exact amounts that we will be adding from one thing to another. This is going to be what we're going to be doing in lab. And so we can take a look at it right here. But basically, we have one of these two is going to be an unknown concentration. It depends on which one it is, but we will put some kind of value, some kind of, one of them is going to be known. We'll know the molarity and the volume of one. And in this, we will either know the is the molarity or the volume. We'll use an indicator to be able to tell when this is complete, and so that's how you can see this color change, and we will be able to see the exact volume that we need to add in order to get a color change to occur. Okay, and so this is the last question, so let's go through exactly how we would do a volumetric analysis. So if we have a flask, like we did right here, containing an unknown amount of hydrochloric acid, and we can titrate it. So titration is this process right here. It's adding one fluid to another until the color changes. With 2.07 molar NaOH, it takes this amount, so we know our volume and concentration. We want to determine the mass of hydrochloric acid that is going to be present in that flask. And we want to determine the stoichiometry of the reaction by writing a balanced equation. We have NaOH and HCl. This is going to give us our stoichiometry. We will balance it, and it's already actually balanced. And this is how we'll do it. We'll take the amount, the known amount. We'll take the concentration in molarity. We'll use the equation, stoichiometry, and then we'll use the molar mass. And then out of this, we will get the amount of grams of HCl. Okay, that's all I got for you today. I will upload more when I have time to. Bye-bye.